Today's topic is deep learning scaling is predictable empirically, and my name is Kamran Ali. The motivation behind this work is to address this very important question, which we all deep learning practitioners come across, is how can we improve the state of the art in deep learning, or how can we improve the model accuracy. So the deep learning recipe that we follow is to search for improved model architecture, or to create larger training data set, or to scale the computation speed. The motivation behind this work is also to have a deeper understanding of the relationships between training data set, computational speed, and model improvements or model improvement in terms of accuracy. So the objective is to find reliable ways to improve the model accuracy, because we all know that the model architecture search for improved accuracy depends on epiphany. We all know that. And although it sometimes creates better improvement in terms of accuracy, but it requires complex reframing of the modeling problem, and this task requires sometimes weeks or even months of testing. So the other motivation behind this work is to emphasize on the significance of having larger data set and its impact on model accuracy. So they conducted a large-scale study, and this large-scale study shows that the accuracy scaling is predictable with enough data set and computational power to train larger data set. And they used various application domains like machine translation, language modeling, image classification, and speech recognition. The methodology that they used in this study is that we have a model and we train it on a subset of a data set, and we analyze the accuracy or the performance of that model. If the performance is good, then we add more training data to that. If the performance is not good, then we increase the model size or make the model size bigger. So we do this iteratively. By doing this study, they came up with a relationship or learning curves which says that the generalization error scaling follows a power law, which is given by this equation. In this equation, epsilon, which is a function of m, epsilon is the generalization error or validation error, and small m is the training data set. Alpha is a constant, and as we can see that the generalization error according to this equation follows a power law with exponent beta g. So this power law exponent beta g has a range from minus 0.07 to minus 0.35. And they found it empirically. So if we plot this relationship using the log graph, we get a straight line. Beta g, which is the exponent of the power law, is actually the slope of this line. So the larger the value of the beta g, in other words, the larger the slope, the better the relative loss improvement. By doing this large-scale study, they also came up with a model size relationship given by this equation. In this equation, small s is the size of the model, which is a function of m, small m, which is the size of the training data set. And it also follows a power law with exponent beta p. So if we plot this relationship, we see that the best model size, small s, grows sublinearly with data. So this is not the first time that they came up with these relationships. These relationships have been proposed in theory by prior work, like Amari et al. In 1992 suggested that the generalization error should follow a power law with exponent beta g. But the theoretical range for beta g power law exponent is from minus 0.5 to minus 1, which is inconsistent with the beta g range that they found empirically in this work. So let's talk about the experiments that they performed. Let's talk about neural machine translation experiments that they performed. In neural machine translation, the input is in the form of text in a certain language, in this case German, and we feed it to the neural network, which is machine translation network, and it gives us output in the form of text or command, or in the form of text, which is in this case English. So they use German to English translation dataset. In this experiment, they wanted to verify a theoretical concept which says that the generalization error epsilon of a fixed size model follows power law, but as the capacity of the model, fixed size model, exhausts, it deviates from the power law trend with an error gamma. So in order to validate this theoretical concept, they did an experiment, and they fixed two LSTM networks, one with fixed number of hidden units per LSTM layer, like 208 hidden units per LSTM layer, and the other fixed model that they used contains 512 hidden units per LSTM layer. So as it can be seen that both of these two models follow the power law for a certain period, but it deviates from the power law trend after a certain amount of data set. And the error rate that is given in the equation by gamma is at, as it can be seen, 0.39 for one model and 0.32 for the second model. So the first LSTM model with having 208 hidden units followed the power law region for a small region. And the larger LSTM network having 512 hidden units followed the power law for a bigger region as compared to the previous model. In another experiment, they did not fix the size of the model. They changed the model size as we talked in the methodology with the training data set. And they obtained this curve, as you can see. But this curve, this composite curve, also drifted away from the power law trend after certain amount of data set, which is on the larger side of data set. So having a larger data set, this composite model drifted away from the power law curve. So the authors argue that this learning curve can be brought to follow this power law trend by having more computation to search for more hyperparameters. And as we can see that the power law region that this best fit model followed is larger than the previous fixed size models. The other domain is the language modeling. And let's first talk about word language models. In word language models, we aim to predict the probability distribution for the next word conditioned on the previous text input. Billion word data set is used in this experiment. And in this experiment, they used three different model architectures. The first architecture consists of 2-layer LSTM. And the second one contains 4-layer LSTMs, and the third one is recurrent highway networks with depth 5. So as it can be seen that all of these three different model architectures followed the power law. And the surprising thing is to see that the power law exponent of these three models are quite similar. So what does it mean? It means that all these three models having different model architectures have the same loss improvement rate. It does not improve the loss improvement, enhance the loss improvement. Another thing worth noticing is that as the training data set grows, these three models, the learning curve of these three models tend to drift away from the power law region. So again, the authors emphasize that this can be brought to follow the power law trend by using more computation. The graph in the right side is shows the relationship between the size of the model with the data set. And as it can be seen that all of these three models follow the power law, and the size of the model increases sublinearly with the data set. But it is worth noticing that the 4-layer LSTM has a power law exponent bigger than the other two models, which suggests that the 4-layer LSTM, although it has many parameters, but it cannot use them efficiently. The other language model is the character language model. In character language model, the aim is to predict the probability distributions for the next character conditioned on previous sequence of input text. And in this particular experiment, they used the model architecture of recurrent highway networks, but they changed the optimizers, like they used SGD and they used ADAM. They used two different optimizers for this recurrent highway network, depth 10 recurrent highway network. So what they found that these two models with different optimizers follow the power law trend. And the power law exponent, as we can see that the power law exponent of these two models are quite similar to each other. So it suggests that the changing the optimizer also does not improve the loss improvement rate. But it is worth noticing that the model with ADAM optimizer shifted this power law curve downward in the y-intercept, which suggests that ADAM is better in this case. The graph in the right side shows the scaling of the model size with respect to data set. And as we can see that they follow sublinearly the power law trend. But the model with ADAM optimizer requires more parameters as compared to the SGD. The third domain is image classification domain. And in image classification, the task is to classify image. And in order to achieve this task, we input an image to the network and we get the probabilities associated to the labels. And we choose the label with the highest probability. So in this experiment, they used the ResNet model. And in order to scale the size of this model, they changed the number of layers from 10 to 200 layers. And they also changed the number of convolutional filters to modulate the model size. And they used ImageNet dataset for this task. In this experiment, since the model architecture is ResNet, what they changed is the error loss matrix. And they used 3 error loss matrix, average cross entropy, top 1 classification error, and top 5 classification error. And as we can see that these 3 error matrix based models followed the power law after a certain amount of data set. And in the smaller region, as we can see, these 3 models failed to follow the power law trend, which suggests that the models failed to model the data distribution having a smaller data set. The graph in the right shows the scaling of ResNet model with respect to the data set. And as it can be seen that this learning curve grows sublinearly with the data set. The third domain is speech recognition, and in speech recognition, the input is acoustic speech signal. We feed it to the speech recognition based networks, and we get text as an output or any command as an output depending on the application. So So in this experiment, they used two different model architectures, which is DS2, deep speech 2, and the second one is attention-based model. And as it can be seen that both of these two learning curves follow the power law trend. And again, the learning curves drifted away from the power law trend at the larger training data set size. And at this region, the model size is also bigger. So again, we need more computational power to search for more optimal hyperparameters to make this curve follow the power law trend. But the surprising thing is to note that the beta g, which is the power law exponent of both of these two models, are the same, which is minus 0.3. So again, it shows that having different model size does not enhance the loss improvement rate. But the deep speech 2 model shifted this curve down in the y-intercept, which shows that deep speech 2 model is better than the attention model in this case. In another experiment, they took the deep speech 2 model and they fixed the size of deep speech 2 model for 1.7 million parameters, and for 6 million parameters, and for 87 million parameters. And they also reported the best fit learning curve for this particular model, deep speech 2 model. And as it can be seen that the model having the largest number of parameters, 87 million parameters, performed better, and it followed the power law region for power law trend for a higher region, and it is closer to the curve of best fit results. And the model with the smallest number of parameters, which is 1.7 million parameters, followed the power law curve for a smaller region and then drifted away from the power law curve or trend for a smaller region as compared to the previous one. So the implications of the power law is that the predictable scaling can be used to do model and optimization, debugging, and iteration time. And we can estimate the impactful next steps to improve the model accuracy because it's predictable. So how can we improve the model search architecture? If we have a model and it gives us the power law learning curve like this one in the red, and if we change the model architecture and it gives us a learning curve in such a way that it brings the power law trend or the learning curve down in the y-intercept, then it means that this particular model architecture is better than the previous one. During this study, they found that the learning curve can be characterized into three regions. The first region, which they name small data region, is the region containing, corresponding to the region having the smaller data set. And in this region, they found that, and as we saw in the results, that the model's accuracy improvement was very not good as compared to the power law region. So they say that the accuracy improvement in this region is as good as best guess or random guessing. The second region is the power law region, in which the models follow the power law trend. And the third region is the irreducible error region. And in this region, the authors mentioned that there is an irreducible error associated to each problem, at which the model accuracy plateaus or it does not change. And it is almost impossible to overcome or to go beyond this accuracy or beyond this error. And it is due to the fact that there are certain limitations like mislabeling of the data set or some inherent properties to the model that is that needs to be addressed in order to overcome this. So what we can conclude from these experiments is that data is very important. And if we need more scaling in terms of accuracy, then we need more data. But we also know that the cost of collecting and labeling data set is very high. It is mentioned in the paper that predictable learning and model size curves may offer a way to project the compute requirements to reach a particular accuracy level. So what does it mean? We saw in the previous experiments that most of those learning curves drifted away from the power law trend. And we can bring these power law curves to follow the power law by using more computational speed or more computational resources by searching for optimal hyperparameters. The other implication is that achievable errors follows Moore's law. And we know that Moore's law says that the computational speed increases with time. So how it follows Moore's law, let's see, if we have an acceptable error, let's say at this point, and if this acceptable error requires a large amount of data set, then we need to increase the model size. And as we saw in the previous slides, that at the larger data set region, the learning curve trend drifts away from the power law trend, and we need more computational power to search for optimal hyperparameters. And in order to do this exhaustive search, we need more computation speed. So in other words, achieving this error or achieving this accuracy depends on time. Because if we have that computation speed, then we will be able to achieve that accuracy. The third implication is that requirements are predictable. Now we can predict how much data we need to acquire a certain accuracy and how fast computers need to be to achieve an acceptable error. The third one is that model architecture search can be done in a reliable way, in a reliable, faster, and cheaper way. Because we can do this using the smaller data sets. And if the model architecture for a smaller data set brings the learning curve down in the y-intercept, then it means that the model is accurate and we can use it. So we follow a search and then scale strategy. Let's see this in a graphical way. As it is suggested that we can do model search in the smaller data set region, which is fast and cheaper to do that. If we find a better model, then we scale it and add more training data and train it and validate it. So across the applications, we find that the power law curve exists across all applications, model architectures, optimizers, and loss functions. We also find that for a single application, different architectures and optimizers show the same power law exponent. Best fit model size grows sublinearly in the training data set. We saw empirically. And this relationship is also predictable empirically. Thank you.